Morning everyone. A very good morning. Shall we begin the session? Today's topic is chapter number 8, that is RDBMS, that is the Relational Database Design. Yes, last two classes were cancelled due to the reason that I am not available over here. I am going out of town. So that's why the class is cancelled. So that is not an issue. We will continue this class by same topic that we have left in the Friday's class. So Saturday, Sunday is a weekend. Monday, Tuesday there is no class. So after 4 days, today is the class. So chapter number 8 is relational database design. How we can use the RDBMS or how we can use the relational database design in which we are designing a schema, and many of the issues are also used to design the database part, and in which there are many parts in which we can use the database design, in which we can use the database schemas. So let's move with the relational database design. That is how it is moved or how it is used in the relational database design that provides a schema for the relational databases. And many of the issues in doing are so similar to the design issues that we consider. And in general, the main goal is to inform, or main goal is to make the general set of the relation in which the schemas are used for the relationship. That includes how the information will be gone, how it will be carried out within the data in a normal form. So this will be accomplished by the appropriate normal form, that may be a normalization, that may be done with a normalization. So we need information about the real world enterprise that we are modeling with the databases, and some of this information exists in a well-designed ER diagram that is represented by the ER diagram, that is the entity relationship diagram, but additional information about the enterprise may also be needed as required. In this chapter, we introduce a formal approach to relational database design based on the notion of the functional dependencies. What are the various functional dependencies that is accomplished with the RDBMS, that is a relational database design, and we then define normal forms in terms of the functional dependencies and other type of data dependence. First, however, we view the problem of the relational design from the standpoint of the schema derived from a given entity relationship design. Now, next is features of the good relational design. So our study of the entity relationship design provides an excellent starting point for creating a relational database design, how it is used, how it is gathered, and how it is possible to create or set up the relation schema directly from the ER diagram. And obviously, the goodness or the badness of the resulting set of the schema depends on how good the ER diagram or ER design was the first place. So this depends on the requirement of the user. So that depends on the requirement of the analysis, how it is used, how it is formed with the ER diagram, how it is used to make the ER diagram with the code that is available in the collection of the relation schema. And however, we can go a longer way towards a good design using concept that we have already studied. And for the ease of reference, we repeat the schemas for the university database in this figure. That is a figure that is given. This is the classroom, building room number, capacity, then department, department name, building budget, then course that have a course ID, that have a title, that have a department name, that have a salary. Then there is a section, there is a course ID, section ID, semester, year, building, room number, title slot ID. Then teachers ID, course ID, section ID, semester, and the year. Then student ID, name, department name, total credit. Then takes, that is the ID, course ID, section ID, semester, year, and grade. Then advisors, that is the SID and IID. Then time slot, that is the time slot ID, day, start time, and the end time. Then prerequisite, course ID, and the prerequisite ID. Now next is the design alternative, that is the larger schema. We can also use larger schema for some alternatives that is used with the schemas, instructor and the department. So we have a schema, instructor, department, ID, name, salary, department name, building, budget. So this represents a result of the natural join on the relations corresponding to the instructor and the department. And this seems like a good idea because some queries can be expressed using the fewer joins until we think carefully about the fact that the university that led to the ER diagram. Now let us consider the instructor department relation that we is used to expect, or that is used to repeat the department information, that is the building and the budget. So once for each instructor in the department. For example, when I talk about the information about the computer science, that computer science department will be used for the building for the instructor in the department. For example, when I talk about the information about the computer science department, that is the tailor and the 10,000 or 1 lakh, that is included in the tuples of the instructor, that is the cats, Srinivans, and the brand. And that is also possible that all these tuples agree to as the budget amount, since otherwise our database would be inconsistent. That is included in the database design, that is included in the database for the instructor for the design part. And even if we decided to live with the redundancy problem, that is, there's the duplication problem, there's still another problem with the instructor department schema. Suppose we are creating a new department in the university. So in the alternative design above, we created this design. We cannot represent directly the information concerning a department unless that department have at least one instructor at the university. And this is because tuples in the instructor department table require the value for the ID, name, and the salary. So this means that we cannot record the information about the newly created department until the first instructor is used, until the first instructor is going on with the requirement of the users. There's ID, name, salary, department name, building, budgets. So there are 6 fields over here, that is instructor department. In the old design that we have studied about, that's the schema department can also handle this. But under the revised design, we will have to create a tuple with a null value for the building and the budget. And in some cases, null values are troublesome, that is, that makes the duplication, as we saw in our study of the SQL. And if we decide that this is not a problem to us in this case, so we can proceed to use the revised design. The next is design alternative for the smaller schema, for the smaller design, that we have started out with the relation with the schema instructor department, and how would we recognize that it requires the repetition of the information and should be split into 2 schemas, that is the instructor and the department. And by observing the contents of the actual relations on the schema, the instructor department ID, we could note the repetition of the information that resulting from to the list of the buildings and the budget once for the each instructor associated with the department. However, this is the unreliable process that is not possible with the department with the attributes, that is also used with the real world entity, that is also used with the real world scenarios, that makes the schema, that makes the larger objects with the smaller objects. And the number of tuples can be used, can be in the millions or the higher, and discovering the repetition would be the troublesome, would be the guess out, that will be very costly, and there is even more fundamental problem that is used with this approach. With the lack of the information, that is the administration of the general rule. And in our example, we would know, how would we know? In that university organization, each department must reside in a single building and must have a single budget amount. And it is in fact that we use the single amount that is with the same budget or the coincidence. And in particular, we will need to discover that the university requires every department must have one building and the one budget value. And in case of the institute department, a great process of creating a near diagram successfully avoided the creation of this schema. However, this fortune or this fortuitous condition situation does not always occur. This does not always occur. Therefore, we need to allow the database designer to specify the rules such as each specific value for department name that correspond to at most one budget. That correspond to at most one budget means that correspond to each and every time that is required for each budget that is required in case the department or where the department is not a primary key for the schema in the question. In other words, we need to write a rule that says if there were a schema, department name, budget, so we use that department, we use that budget within the schema that require the database design. In other words, we need to write a rule that says if there were a schema that the department name budget, that will be included to observe as a primary key, that is the department name and the budget. And given such rule, how we can use, or we now have a sufficient information, sufficient requirement, sufficient database design that is used with the functional dependency and the rule that results from them, that allows the database designer to recognize the situations where a schema, object, or O to be split or decomposed into two or more schemas. It is not harder, but it's not hard to see that this relation will be in the right way to decompose the instructor department, instructor ID into the schemas, instructor and the department as in the original design. And finding the right decomposition is very much difficult or harder for the schemas with a large number of attribute and several functional dependencies. To deal with, we should rely on a formal methodology that we developed in this. So not all decompositions of schemas are useful. So consider an extra case where all we have the schemas consisting of the one attribute. So no interesting relationships of any kind could be expressed. That will be the next extreme case that we studied, where we choose to decompose the employee's schema. There is the employee, there is the ID, then name, then street, then city, then salary. Into the following two schema, that is employee 1 and the employee 2. And the flow in this decomposition arises from possibly that the enterprise have two employees with the same name. This is not unlikely in practice, as we cultures have certain higher popular names and each person with a unique ID that also tells about what is the ID, how it is carried out, and why ID can serve as a primary key. And as an example, let us assume two employees, both named Kim, work at the university and the higher tuples in the relation on the schemas employed in the original design. This is the ID, this is the name, this is the natural join process. The next is atomic domain in the first normal form, that is a lossless domain, that is the first normal form that is used. So the first normal form of the atomicity works with the attribute that some degree of the substructure that specifically allows multi-valued attributes such as the phone number in the attribute, phone number in the value, phone number in the database design that must be accomplished with the database values that must be accomplished with a composite attribute with the component attributes. When we create the tables from ER diagrams or ER design that contains these types of attributes, we eliminate this substructure. And for composite attributes, we let each component be an increment or be an attribute in its right way. And for the multi-valued attributes, we create one tuple for each item in a multi-valued set. And in the relational model that we use, we formalize this idea that attributes that do not have any substructure and that is also atomic if each and every element of the domain are considered to be the indivisible units, that is used with the indivisible unit, indivisible content. We see that the relation schema R is in first normal form if the domains of all the attributes of R are atomic. And a set of the names is an example of the non-atomic values. For example, if the schema of a relation employee included as an attribute children, whose domain elements are the set of the names, and the schema would not be or would not be in first normal form. So this composite attributes such as the attribute address with component attributes, street, city, state, zip also have a non-atomic domains. So integers are also used. Integers are also assumed to be atomic. So the set of the integers is an atomic domain. However, the set of all the set of integers is a non-atomic domain. And there's a distinction that we don't normally consider integers to have subparts, but we consider sets of integers to have a subpart that makes the integers up to the use. But the important issue that is considered over here, that is used over here, is not how domain itself works, but rather how we use the domain elements in our database. And the domain of all the integers would be non-atomic if we consider each integer to be an ordered list of the digit. As an practical illustration of the above point, consider an organization that assigns the employees identification numbers of the following form. The first two letters specifies the department and the remaining four digits are unique numbers. When such identification numbers are used, the department of our employee can be found by writing the code that breaks up the structure in an identification number in a code that requires large number, that requires extra programming, that works with the database design. With the identification number. So doing so requires extra programming and the information that gets encoded in the application program rather than in the database. Further problem also arise if such identification numbers are used as a primary key. And when an employee changes department, so the employee identification number must be changed everywhere it occurs, everywhere it's used, which can be a difficult task, which can be a narrower task, or the code that interprets the number that would give us a wrong result. The next is decomposition using functional dependencies. How we can decompose with the letter with the unique word that must be decomposed within the domain area. So we use the Greek letters for such attributes. We use the relation schema, that is a set of the attributes in which we can define the R, that is a set of the attribute, but also sometimes simplify the attributes within the domain, within the value in which it occurs, in which it rotates. So when a set of the attributes is a super key, we denote it by K, and the super key pertains to a specific relation schema. So we use the terminology K is a super key of the R. So we use a lowercase name for the relations, and in our example, these names are intended to be realistic. For example, instructor, while in our definitions and the algorithm, we use single letters like R. Our relation, of course, have the attribute or has a particular value at any given point of time that must be used within an attribute that must be used within the database. That is used within the relation, that is used with a particular value at a given time. So that refers to an instance, or that refers to a value that uses the term instance of the R. When it is clear that we are talking about an instant, we are talking about the value that uses the term instance of. And when it is clear that we are talking about the instance of R that is used with the relationship, that is used with the database R, we simply use the relationship name. The next is the keys and the functional dependencies. So database model a set of the entities and relationships in the real world, and there are usually a variety of the constraints, rules on the data in the real world that is used are expected to be held in university database example. One is the student and the instructor that are uniquely identified by their ID, and each student and the instructor have their own name, and each is associated with the database. Each is associated with only one department. Then each department has only one value for its budget, for its value, and one associated building. And there is an instance of a relationship that satisfied all such real-world scenarios, since constraint that is known as the legal instance of the relation. The legal instance of a database is a one where all the relations or instances are the legal instances. And some of the most common used type of real-world entities constraints can be represented formally as a keys or as a functional dependencies, which are defined over here. Then we define the notion of a superkey or a subset as a set of the rows or one or more rows attribute that we taken collectively that is used to identify the uniquely a tuple in the relation that is defined in the query that is defined